Hello, everyone. This is the palindromic day. Today, our speaker is Kadri İlker Berktav, who's currently at METÜ. His thesis advisor was Ali Ulaş Özgür Kişisel, and he's going to give us a talk on symplectic structures on derived states. Let's welcome him.
Okay, so thank you for the introduction and having me here today. Actually, it's a pleasure to be part of this seminar series. Okay, fine. So as you know, so this will be a talk or an overview on this subject, derived symplectic geometry. And basically, I will be interested in local models for this geometric structure, basically. But of course, there are many details. I just skip some details to save some time. But we will see. Okay, it will be a kind of a brief talk, okay, about the subject. And let me start with a couple of references, as you see, a couple of them, and a little bit history. And actually, this one, so let me just highlight, and then I will present you the outline and we will start the main subject. And this paper, actually, this one is the main paper of interest. I mean, actually, this is the original paper where the concept of shifted symplectic structures were introduced. And actually, the idea, I mean, I'm not an expert, but the idea is not that much new. I mean, it's a kind of an old idea, but what is new? It's a kind of a new systematic presentation of the subject by using the language of derived algebraic geometry, okay? And in this point of view, it's a kind of a foundational paper, okay? So this one, it's very important. And there are many important results, existence results and proofs in that paper using derived algebraic geometry, basically. And of course, speaking of which, what is derived algebraic geometry? In this talk, I will briefly explain the derived algebraic geometry, okay? And very roughly speaking, there are many equivalent approaches. So the one is Tuen and Vezozzi's approach, theory of derived algebraic geometry, these two papers. And the other one is Lurie's work, okay? And these two approaches are in some sense equivalent in some way. And of course, they are very involved. But in this talk, we will just borrow some main tools, okay? Just discuss main and key ideas from derived algebraic geometry. But as I said, our main purpose, our main aim is to discuss possible geometric structures on derived spaces, okay? So the aim is possible geometric structures on those derived spaces, on derived spaces, okay? And of course, to be more specific, we are going to be interested in explicit local models, okay? So explicit presentations. Explicit presentations for those structures, which actually, this is exactly the place where this paper, the second one here, this one enters the picture. So we will follow this paper actually. I mean, Bro, Busse, and Joyce, they give the local models for this, for those structures, okay? And then as you see as an outline, we will first discuss our main algebraic setup, okay? And then I will revisit basic aspects of derived algebraic geometry. And then we will see derived symplectic geometry, okay? So this is more or less a kind of a motivation. Okay, so let's start. So what kind of algebraic setup we have? Okay, so the first one. Actually, the main object is this category, the category of CDGA. Okay, so this is basically the category of commutative differential graded K-algebras. Okay, in non-positive degrees. Okay, something like this. So what are the objects? Objects are, so we will denote objects like this, A dot in general. So this is our convention. It means that we have some graded part. So it's a kind of a graded K-algebra. And we also have a differential. Okay, so it's a kind of just a graded module, if you like. So we have some kind of a grading like this. Of course, there are some multiplication, associativity, some commutativity relations, graded commutativity, whatever it means. And there are some nice properties, okay? And we have this differential here, D. Of course, it satisfies, the Leibniz rule. It commutes with the structure, everything goes smoothly. So it's fine. So it's a kind of object like this. What about the morphisms of this category? It's a kind of a, as you may expect, these are just maps from A dot, let's say B dot, but and commute with all structures. Commute with all structures. So these are component-wise defined. F is just like this, Fi, and each Fi is a map from ith homogeneous part to B, the other CDGA, okay, Bi. Okay, these are just homogeneous parts in degree I. And actually, this is a little bit cheating. So, here we have a remark. Actually, we are using the homotopy category of this thing. Actually, we are interested in, we just consider the homotopy category of this category. CDGA, K, concentrated in negative degrees. Okay, and this is obtained by, the usual localization procedure by the weak equivalences. CDGA, K, negative, and here, this is the weak equivalences. We just, formally inverting everything. So here we have weak equivalences. So these are just quasi-isomorphisms. Okay. So this is our weak equivalences. And then, but by using, by abuse of notation, we always use CDGA, the same notation for this homotopy category, okay? So we have a kind of a abuse of notation. Also, whenever I use tensor product, okay, it means a derived tensor product, okay? So we have a tensor product, it means this is just a derived version of it. What does it mean? Therefore, the existence of, fiber products, colimits, etc. are no longer a big deal, okay? So everything is nice, so we have everything, okay? And then this brings us the following definition. So the definition. So we have A dot. Let's say this is an object in this category, okay? CDGA, it is said to be a standard form. Okay, standard form. If okay, we have the following conditions. If the A0, right, homogeneous degree 0, is smooth, finitely generated K-algebra. And secondly, second condition, A star, remember the notation, A dot means we have this pair, A star, the graded part, and the differential D. A star is freely generated over A0, degree 0 part, by finitely many variables in each degree. Okay, so what does it mean basically? So what does it tell us? For for instance, the first condition. So what does it tell us? Actually, algebraically, it means that A0 is something like this. We have K, right? So we have a ring in finitely many variables, something like this, over the base field K. Let's say we have, these are the variables, divided by some ID, right? So it means that A0 is finitely presented, right? But geometrically, remember, what does it mean by saying smooth? So the smooth means, if you look at the corresponding geometric object by looking at the spec of this A0, this is smooth, affine, K-scheme. Okay, this is the meaning of this definition. So algebraically, this is something like this and this. What about condition 2? Condition 2 means actually more or less clear. A star is a kind of a ring, right, over A0, and we have many variables, but finitely many, in each degree. For instance, this one goes to m-1. This is, let's say, the -1 degree. And there are variables in degree -2. Let me use this notation, and -2, -2, and goes like this. And finally, we have mk. Each mi is just an integer, finitely many variables we have, and these superscripts gives you the degree. Okay, so this part is degree -1 variables, so these are degree -2 variables, and story goes like this. Okay, so this is the meaning of standard form CBGA. But we have a remark. In general, what we want in practice, we want minimal, some kind of a minimality, minimal standard forms. Okay, we are interested in minimal standard forms, but what does it mean? You can easily guess. It means that each mi here, number of variables in each degree, taken as to be the least possible number. Okay, so each mi, okay.
Just a question. In the variables, when you write these other powers, if we interpret this notation as a polynomial ring of these variables with coefficients here, then the higher powers do not need to be denoted. Then do you mean something other than the polynomial ring generated with coefficients in A0, or do you mean something like only considering the degree -1 terms in the polynomial algebra, or
actually, yeah, I mean, there are some degree 0 terms here, right? Something like this, right? There are some generators also here. And we just consider, so if you like, yeah, I mean, you can consider this variables as well, but this thing is freely generated over A0. Okay.
Okay. So then it isn't x1 to the power of -2 already contained when we write x1 to the -1?
No, I guess. I mean, so this is completely different variables. I mean, some other degree. So these are degree 0, degree -1. So there are some different pieces. I don't know.
Okay. Is it a polynomial? Do we mean the polynomial ring, or the algebra generated with these free generators?
No, free generators.
But then is the generation only in the additive components and not in the multiplicative components? So then we need to explicitly write the other powers. Is it like that?
Yeah, I mean, I couldn't understand some parts now, so sounds getting weirder, but you are right, I guess. Probably I will explain this soon. Okay. It will be clear. Okay. So what else? What else? Let me just continue. Of course, this differential D now determined by, if you look at the action of D on each xij's, okay? When you determine this, you can define D itself, right? And also we can define a new notion of dimension. It's called the virtual dimension of A dot, okay? Which is just the alternating sum, as you may guess, of each this mi's. Okay, so this is a little bit important, and it's very interesting that this thing turns out to be even. Okay, turns out to be even in derived symplectic setup. Right? This is exactly the algebraic counterpart of the situation in the usual differential geometry, right? So in the usual symplectic geometry, right? So due to the non-degeneracy condition on your symplectic form, your manifold must be even dimensional, right? So in this setup, there must be a kind of a correspondence. But what is the correct notion of dimension, which is this? Okay, somehow we obtain a kind of an even behavior visible also here. Okay, so this is another remark. Okay, so that's all. So these are main objects. And by using this A dot, so let us start with some CDGA. Okay, now we can discuss.
MI stands for, MI is?
What?
What is MI?
MI is the number of generators in each degree I.
Okay.
For instance, we have m-1 many variables in degree -1. We have m-2. Maybe notation is a little bit confusing, but these mi's are all integers. Okay, this corresponds to the number of variables in each degree I. Okay. So this thing is the usual module, the A star module of Kehler differentials. Okay, we know this thing. So by using this notion, we can define, so remember, so we just try to mimic the procedure in the usual symplectic geometry or the differential geometry. We need forms, right? Somehow we need to define forms. And somehow we need cotangent space or the analog of it. So therefore, we can define something called the Derived algebra. Okay, which is denoted like this. And this is defined like this. Okay, P0 to infinity and K minus 2 to 0. Exterior power of this A dot. And we have other graded pieces, and we have some shift, which is not important at this stage. But what is important, if you look at carefully, we have two gradings here. Okay, in the usual symplectic geometry, right, we have a Derived algebra, of course, no problem. But in general, we only have one grading. But now we have a kind of a double complex. So P is kind of a weight. Okay, so let's P is called weight, and the K is what was it, degree. Okay, and also we have two differentials. So we have two gradings, and hence we have two differentials. One of them, as you may guess, the usual Derived differential. right? D Derived. And if you look at carefully, it really increases weight by 1. Right? Don't touch the degree. Degree is still K. And now weight is P plus 1. I just skip this part, okay? It's not that much important right now. And D is the internal differential coming from the differential of this A dot. Remember, we have some internal differential. Therefore, it now increases degree by 1. Okay. Okay, something like this. Now here, be careful about this degree. Now be careful about the weights. And of course, they are compatible in some sense that there are many other properties. For instance, D square and D Derived square are all 0. And also there is this anti-commutativity. Okay, something like this. So it's a kind of a double complex, actually. Okay, so you can really have this picture. So let me sketch quickly. So this one, let's say this is degree K part. Let's say this is D, the internal differential. K plus 1, and it goes like this. Okay, so this is the D Derived, and goes like this. This is a double complex. D Derived D. Okay. And of course, you may ask, okay, why standard form CDGAs are important? Okay, so why we care? So here is the reason, remark. So as you see, this is exactly the first place where we diverge from the usual symplectic geometry, right? So now we have a double complex structure and we have some extra internal differential. But in the usual case, we only have Derived differential. Okay, fine. So the thing is, when this A dot is a standard form, is of standard form, actually we have two important outcomes. One of them is the presentation of this Kehler differential. So this is nothing but so a star valued, right? The usual D Derived Xi J. Okay. So this is K and J runs from 1 to Mk. Okay. So this is A star module actually. And as you see, the generators are D Derived act on the usual variables. Remember the variables. And the second important property, and as you see, the first one is really the explicit presentation. And the second one is some characterization of the cotangent complex. So in general, cotangent complex and this the modulo of Kehler differentials are related, right? They are related, but not the same, actually. They are related, but not the same, because this thing, this modulo of Kehler differentials, is not well behaved under localizations by quasi-isomorphisms. Therefore, you need to replace some, you need some cofibrant replacement or something like this. But here, if you have a standard form, they are the same. Okay, this is some theorem, or if you like, so this is some important fact. So therefore, in the case of standard forms, you can really consider, I mean, define a cotangent complex by just using Kehler differentials without using any cofibrant replacement. Okay, therefore this is really practical computation. This gives you a practical computation for the cotangent complex. Okay, therefore standard form CVGAs are good. Fine. Okay, so that's all. So this is more or less the algebraic setup. So let me now quickly revisit some key ideas from dry algebraic geometry, and then we will combine these two. And the idea is, so the main idea, so remember in the usual algebraic geometry, it's really locally modeled on commutative K-algebras, right? If you look at spectrum of this commutative K-algebras, you define a fine scheme, right? Similar here. So a derived K-scheme, let's say, is locally modeled on spec A dot. Okay, so the same idea. I mean, just we generalize the usual algebraic geometric notion. But remember, in general, how to define is, okay, another story. There are many details, but we use functorial approach, right? So how to define? We use functor of points approach. So what does it tell us? If you remember, you can really define, right, schemes, for instance, as a certain presheaves of sets, right? Plus, you know, this descent property. I mean, local to global properties. Okay, this is how we define schemes, right, in a functorial perspective. And actually, you can play with this source and target categories, right? If you remember, if you move to two category theory, and you can discuss two category of groupoids, right? In a very similar, I mean, a very similar spirit, you can define a stack as a certain presheaf of groupoids plus local to global conditions. And story goes like this. So simplicial sets, but now it's the infinite category of simplicial sets. And now you can define higher stacks like this. Okay. So as you see, when you move here from top to bottom, right? What is changing actually structure of points are changing, right? What does it mean? The points of a scheme, right, form a set. But the collection of points of a stack has the structure of groupoids, right? So the structure of points is changing. What else? You have more non-trivial, higher morphisms. What does it mean? Maps between maps between maps, right? The story goes like this. And this gives you the notion of infinite tower of equivalences. Okay? For instance, you may ask when two points are the same, are equivalent, if there exists path between them, right? And then you may ask when two paths are equivalent, when there is a homotopy between them. And then you may ask when two homotopies are equivalent, right? There exists some higher morphism between them. And this is exactly what the meaning of infinite tower of equivalences. Okay? And then if you play with the left-hand side, now we have CDGA, right? So this is exactly gives you the derived stack. Okay? And actually we have a nice inclusion over here because if you have a commutative K-algebra, you can easily see this commutative K-algebra as a CDGA, right? Something like this. Concentrated in degree 0 and with the trivial differential. So therefore, you can trivially see this K algebra as a certain CDGA. And therefore, if you define some spec A here, which is the affine scheme, right? So spec A dot turns out to be the affine drive scheme, okay? Therefore, when you move from top to bottom, the local model, right, is changing, basically. Okay, anyway, so long story short, what is a derived stack? Derived stack is just a presheaf of simplicial presheaf preserving weak equivalences plus local to global property. So a definition. So this thing is just X. It's a kind of a CDGA to simplicial sets. Okay, let's say this is presheaf of simplicial sets, sometimes called simplicial presheaf, and plus local to global property. So this is called derived stack, basically. Okay. And what is a derived scheme? Another definition. And let me denote this category by this infinite category by like this. Okay. And an X in this infinite category is called an affine, is an affine derived scheme, as you may guess, if X is just given by some spec A dot. But of course, what is spec? So only thing I may explain is that there exists a well-defined spectrum functor in this derived setup as well. Okay, we have a spectrum functor, so therefore we can really define a affine scheme like this. And similarly, you can define a derived scheme in a very similar way in the usual algebraic geometry if it can be covered by a Zariski open affine derived K scheme, then you have a derived scheme. Okay. Covered by Zariski open Y in X with, so you have some kind of affine derived cover. Okay. Okay, but this is more or less the basic definitions. Now we have an important theorem, which is very useful. And this theorem tells us the following. So if you have a affine derived scheme, if you have a derived scheme, derived K scheme, if you like, okay, derived K scheme. So by definition, you can find, for any point, you can find an affine derived neighborhood. So this is fine. But the following theorem tells you more. So you can find a more defined neighborhood. What does it mean? Every, so let me write it down, every derived K scheme X is locally modeled on spec A dot. Okay, nothing new. This is the definition. For any point, you can find an affine neighborhood. But now you can make this A dot special for some minimal standard form CDGA A dot. Okay, so you can find a more refined affine neighborhood. So therefore, so what does it mean? So if you have a X, So we have a small x here. So you can find a refined neighborhood U, which is given by spec A dot, but this A dot is minimal, standard form. Therefore, if you are interested in cotangent complex, right, on that point, this automatically can be given by the modulo of Cayley differentials. Now we use the advantage of minimal standard form CDGAs. Okay, this is very important local theorem. Okay, so by using this theorem, we can actually construct an explicit model. Okay, so that's all for some key ideas from derived algebraic geometry. And the third one, derived symplectic geometry. Okay, so let's discuss this. Maybe we should first remember the classical case. Right? In the classical case, let's say X is just a smooth manifold. Okay. Now we have this Lx, which is the cotangent space. And we have Tx, which is the tangent space of X. These are, bundles, I'm sorry. So these are vector bundles. Right? At each point, we have a really honest vector space. And remember how to define a P form. Right? P form on X. How to define this? So this is nothing but a global section, right, of this exterior P power of the cotangent bundle, right? So we have this equivalence classes. And then how to define closed P form. Right? Only differential, only notion of a differential in this classical setup, we just have Derived operator, right? D Derived, omega is 0. And omega is in this, the global section of this exterior power of this cotangent bundle. Right? This is how we define closed P form. But now, in this scheme theoretic version, or this derived version, now in derived setup, remember in classical case we have a honest vector bundles, but in derived setup this thing is not a vector bundle, right? This thing is a double complex. Right? So therefore you need more, so you need actually one has higher cohomology classes. There exists non-trivial higher cohomology classes, not just degree 0. Remember, if you go back to classical case, we are interested in degree 0 classes. But now we have homology classes in degree K. And we have something like this. Okay, not just global sections, but now we have this. Why? Because we now have some additional differential, right? Internal differential. Remember, we not just only have the Derived differential, but now we have an internal differential D. So therefore, we have the following definition. A P form, okay, of degree K, as you see the general version, on X, let's say X is just some affine derived scheme. And because of the theorem above, A dot is just, let's say, the standard form, CDGA, minimal, okay, for P positive and k negative is just, let's say, the omega 0 is in is this element. Remember, degree k, weight p, with the following condition. It must be D close. D is the internal differential coming from A dot. Not deram, but the internal differential D. Okay, be careful. In k plus 1. Okay, now you can easily see where this k comes from, right? This is now, this really defines, since this is a D close, so it really defines a cohomology class. Okay, so this definition really makes sense. Okay, what about the existence result, blah, blah, blah. These are all coming from, remember, the previous, I mean, in the introduction, I mentioned a paper, right? The paper of Pantev, Tuan, and Vezzosi. Whose existence results definitions are coming from this paper, basically. And then you can really define non-degeneracy condition. Okay, a two form of just a second. Okay. Of degree k, let's say omega 0, is called non-degenerate if, remember from the usual differential geometry, if the tangent space and the cotangent space are isomorphic, right? But here we have complexes. Is quasi-isomorphism. Not isomorphism, but a kind of a weaker notion. But this is non-degeneracy condition. This is how we generalize the usual non-degeneracy condition. And then finally, another definition, a closed P form. How we define a closed form of degree K. Okay, on, as before, spec A dot is standard minimal. If, so this is a sequence, not just one element, but a sequence, omega 0, omega 1, dot, dot, dot, goes like this, with each component lies in this homogeneous part. So this is its weight, and this is its degree, k minus 1. Okay, just a second. Let me, sorry, this is I'm sorry. Such that, so here are the conditions. First of all, first condition is d omega 0 is 0. Okay. And the second condition is d deram omega I plus d omega I plus 1 equals 0. Okay. So let's try to understand these two conditions. So what does it tell us? First of all, this first condition, right, tells you that if you have a closed P form, its first component is a P form of degree K. Remember the definition. This is the reason why I use this notation, omega 0. Okay, so closed P form of degree K implies that omega 0 is a P form. Second condition looks complicated, but if you sketch a picture like this, you can easily see what's going on. So actually, this is a double complex. And so let me quickly sketch a diagram. Okay, something like this. Okay, so this is D. Since we act by D, it means that it increases degree by 1, right? Something like this. And we have this Derived. Means that we have P plus I, A dot, okay, P plus I, K minus I, and story goes like this. So this is Derived. If you look at carefully, each component fits into diagonal, right? Let's look at omega I. Omega I lives here. And omega I plus 1 lives here. Okay, if you keep track this operation, d omega I plus 1, and similar here, d Derived, this vertical operation, act by d Derived, something like this, and we want some relation here. But by using compatibility relation and d total, you can easily see that, I mean, after some straightforward computation, this corresponds to d total omega equals 0. Okay, remember d total in the double complex is just d plus d Derived. If you compute, you can see. Okay, therefore closeness is really related to d total, not d Derived. Okay, because we have a double complex. And then finally, a final definition. You can really define if you have a closed, as in the usual differential geometry, if you have a closed two form of degree k and plus non-degeneracy condition. This is exactly the definition of k-shifted symplectic form on affine case. Affine derived case. Okay. And actually, as a remark, you can easily see there exists a natural map from the space of closed P forms of degree K. So let me say this, to space of P forms of degree K. Remember, this is just a sequence. That's just a kind of a projection to first component. Okay, this is the space of closed P forms of degree K. This is the space of P forms. So therefore, it's a kind of a systematic formulation or generalization of the usual differential geometric notions to this algebraic or derived setup. So we can really, in a meaningful way, we can define a notion of P form of degree K. Therefore, the usual P form in the smooth setup is just a form of degree 0. Okay, so the degree 0 part of this construction, all of them, corresponds to usual differential geometric notion in the usual manifold theory. Okay, all of them are just degree 0. So if you go back and look at the definition here, this condition is trivially satisfied, right, in the underived case. Because remember, in the underived case, if you go back, remember this inclusion. D is already 0, right? Therefore, in the underived case, this definition still makes sense. And we need this hidden condition, which is automatic in the underived case. But in this non-trivial case, we need to put this condition by hand. Okay, so let me show you a couple of examples. Some examples and results, maybe. Some examples. For instance, first example is -1 shifted structures. Actually, they are quite handy. Okay, -1 shifted symplectic derived spaces are handy. For instance, if you look at the critical locus, the derived critical locus, crit f, of a regular function, okay, let's say f from M to A1, or any open neighborhood, on a smooth K-scheme. This thing, this object, has -1 shifted structure. Okay, this is not the usual symplectic manifold, but this is -1 shifted symplectic derived space. Another example, if you look at the derived intersection, L intersection M, of smooth Lagrangians, okay, in an algebraic symplectic manifold, let's say n omega. This is again a -1 shifted symplectic derived space. Okay, so this space admits -1 symplectic form. Other non-trivial example, so if you are curious, the moduli space, the moduli scheme M of stable coherent sheaths on Calabi-Yau threefold also admits the structure of -1 shifted structure. Okay. Maybe let me just explain first two items here in a more intuitive way. So something like this. So let me just explain. So you will immediately understand what is the relation between critical locus and this derived space. So actually, if you have a smooth manifold, let's say M, okay, smooth manifold, and let us consider X, Rx is just a cotangent bundle. Okay, so let's say a free sheaf. So it has a 0 shifted symplectic structure. So F is just some M. It's a kind of a regular function. And actually the critical locus of F can be defined by using intersection theorem. This is just the intersection of the graph of df with the 0 section of this tangent bundle inside the tangent bundle. Okay, so this is the intersection of the graph of df with the zero section of this cotangent bundle inside T star M. Okay, so actually this makes sense because if you consider this picture, so let's say this is M, okay? Let's say this is our cotangent bundle on that thing, okay? Something like this. Okay, so of course, so we have this embedding, right? So you can embed M itself inside this cotangent bundle, right? By using the zero section, right? By using this zero section. So you have this embedding. So what about DF? DF is another section, right, of this cotangent bundle. So let's say, for instance, something like this. It hits this blue part, and it goes like this, right? It goes like this. I don't know, right? Something like this. So this is the image of DF. As you see, this intersection points are exactly the critical locus of this F. Algebraically, this is just a fiber product, right? So we have M, so T star M, we have DF, we have this zero section, M, so this is the fiber product, M inside T star M. Okay, this is the critical locus. Okay, and actually this DF defines a Lagrangian. So let me combine the second item here. Actually, this DF, any one form define a Lagrangian submanifold inside this. So actually, this is a kind of a Lagrangian defined by DF. This is another Lagrangian defined by the zero section. So intersection of these two Lagrangians, derived intersection, right, has a -1 shifted structure. Okay, so this is zero shifted, and this is -1 shifted. And this picture is true in general. So there is a general result. For instance, general. If you have a K-shifted symplectic derived space here, if you have a K-shifted, then this turns out to be K-1 shifted. So more general statement is also true. Okay, I just skip this statement. If you have some kind of a K-shifted symplectic derived K scheme instead of this cotangent bundle, and if you have two Lagrangian like this, then the intersection turns out to be K-1 shifted. So more general statement is true. Okay, so something like this. So this is another example. Okay, actually, I was planning to discuss some elementary construction like Darboux-like local models, but I don't have much time. Maybe just some keywords. Actually, with this discussion, one can really construct an algebraic model. I mean, Darboux-like local charts, let me say. It is really possible because when you have minimal standard form CDGAs and you have many generators, remember, in different degrees, you can play with them and you can really construct a model, Darboux-like chart, for a given symplectic derived K scheme. So what does it mean when you have a symplectic derived K scheme? It means that locally they are actually the same. So locally you have one specific local model up to some equivalence. So if you have a general symplectic derived K scheme, so you can really find a Darboux-like local chart. a very generalization of the usual symplectic geometry. Remember, in the symplectic geometry, any symplectic manifold, any two symplectic manifold are locally the same. So symplectic structure, there is no local, you cannot distinguish locally. Therefore, you need to look at the global properties, because locally you can always find a Darboux-like chart. Okay, so the similar kind of statement true in this generalized setup. So sometimes it is called the generalized symplectic geometry, because it really generalized the usual symplectic geometry in the smooth category. Okay, fine, maybe I should stop here. So thank you very much.
Thank
Any
you
questions or comments? Okay.
Now, if there are any questions, with the -1 shift, if repeated twice, is it can it be related to the condition for complex manifolds or the Cauchy-Riemann equations in that case? Or can you maybe a little bit elaborate in the particular case of symplectic structures and complex manifolds?
There is a relation between this complex structures and this -1 shifted business. I mean, there are some works of Turn, I guess, or Pantev, and Joyce also study these things in terms of this complex geometric perspective and this -1 shifted perspective. There are some relations. I'm not that much expert on that, but there are some relations.
Okay, but in the last one, this is true regardless of even dimensions, or right? Or
last one, which one?
This is still a symplectic manifold.
Yeah, yes, still a symplectic.
Any smooth manifold or symplectic manifold?
No. M is smooth manifold. This is any smooth manifold, but the cotangent bundle is symplectic manifold.
Okay.
Okay. And actually, by using the definition of, this is the zero shifted symplectic space actually. So K equals 0 case corresponds to K equals 0 case. So this is symplectic. It corresponds to 0 shifted.
Wait, K is the amount of shifting.
Sorry, I couldn't hear.
K is the amount of shifting in general. Yeah, okay.
I guess there are some similar statements for this example. For instance, some moduli space of something else turns out to be a K-1 shifted symplectic thing or something like this. Some ugly spaces turns out to be some kind of a shifted symplectic derived space. And there are some examples and studies on that. And one of the main motivation is actually is to understand the quantization, for instance. So once you have this symplectic structures, then you can ask, what about Poisson structures? There are Poisson structures and local models. And then by using this Poisson structures and symplectic structures, can we reformalize the notion of quantization, for instance, by using this derived business. So I guess this is, there are many results here that I'm not that much aware of, I'm sorry. But there are some examples, important examples of that things.
Okay. Are there any other questions? I'll stop the recording and then let's thank the speaker.
Thank you, İlker. It was a very nice talk, very interesting. Yeah, thank you.